Gotta love the music too.
Compound interest is the interest an investor earns on his original investment, plus all the interest earned on the interest that has accumulated over time. It is easier to think of compound interest as interest on interest. To understand compound interest, let's first look at simple interest, the interest earned on the original principal only. Suppose you deposit $10,000 into a high-interest savings account at a 5% simple interest rate for 3 years. The interest you earn each year is 5% times $10,000, which equals $500, for a total of $1,500 of interest at the end of year 3. $500 plus $500 plus $500. Now instead, suppose that you deposit the same $10,000 at 5% interest compounded annually. In year 1, the interest you earn is the same, $500. But in year 2, the interest you earn is 5% times $10,500, the original amount plus the interest you earned in year 1. So the second year's interest is $525. In year 3, you earn 5% interest on $11,025. $10,000 plus $500, year 1 interest, plus $525, year 2 interest, for an interest payment of $551.25. In total, you earn $1,576.25 in interest over 3 years with compounding interest versus $1,500 with simple interest, a difference of $76.25. The effect of compounding becomes especially powerful over longer time periods as the amount of earned interest becomes larger and larger.
Oops. Okay. So, exactly. Yep. The earlier the better. And if you look at these green histogram bars, check out how they're growing over time. I mean, it doesn't really look like a whole lot, at first, but over time, the gap just widens, and you end up getting exponential growth with these investments, provided you don't do some withdrawing, so down the road or anything like that. But, if we just put the money in the bank and allow, compound interest to do its thing, it doesn't seem worth it, in the first 10 years maybe, but man, it begins growing like wildfire over time. So yeah, the earlier the better. That's definitely a good point there, Robert. But the histogram bars, they follow an exponential pattern, and I'm going to present to you a formula that is basically exponential in nature, which can help us predict how much money would be in the account under compound interest after a period of time. Before that, though, I'll provide you the formula for simple interest. And I believe we touched on this formula way back in the beginning of the semester when we were working in Chapter 1. Just a quick recap, simple interest is really just a one-time calculation where you define the terms of the loan, you decide on how much money you need to take out, you put some information into the computer system, it assigns you an APR, a rate, and then you determine how many years you're going to need the loan for, and then the additional money that you would owe, at the end of the loan, basically a fee for borrowing money, is calculated by taking the principal, multiplying it to the rate, and multiplying it to time. I equals PRT. And this will help you figure out how much additional money is owed should you take a loan out under simple interest. Compound interest does provide additional money that is owed at the end of a loan, but how it's calculated is drastically different than simple interest. With compound interest, there's kind of like this layering effect where it's interest on interest. And I believe that was mentioned in the video. And basically what happens is, under simple interest, you have a fixed amount of time to pay a loan back. And that's the case with compound interest as well. But simple interest is essentially a one-time calculation, whereas compound interest does multiple calculations throughout each year, that you're having the loan out for. And each time that you do a calculation, it's based on the most recent calculation. And so the net effect of that is typically having to owe more money at the end. Or, on the flip side of the coin, excuse the pun there for once, if you're investing, you end up making a little bit more with compound interest than you do with simple interest. Now there's a formula that can help us predict how much money would be in an account at the end of a period of T years under compound interest. And it's got a few variables in it. A stands for the ending amount, okay, how much is in the account after, you can think about. P, which is the starting amount, principal, okay, how much you're walking into the bank with, or how much you need to borrow from the bank. And then we have what appears to be an exponential base, just kind of a little bit more elaborate than what we're used to. 1 plus, and then lowercase r is the percentage rate divided by n. And if you look underneath, n represents the number of times per year interest is compounded. So I mentioned that interest is calculated multiple times throughout each year. N tells you how many times per year that interest is going to be charged. And then the exponent is the product of n times t. I'll explain more on why this is all set up the way it is when we get to a specific example. I think it's a little easier to understand it that way. But let's just make sure that we understand what each variable represents, just to kind of recap it. A is the final amount, P is the principal, the initial amount of money, R is the rate, which we'll want in decimal format versus percent format. N is the number of times that interest is calculated each year. And then T is time in years, okay? And it's pretty critical that we always work in years with financial models, all right? In the next section, we're gonna kind of loosen that restriction and allow T to be any time unit. There's some pretty common values of N that are used with this formula. And which value you use is based on the verbiage in the problem. If it says compounded annually, then interest is just going to be charged one time each year. Semi-annually means that interest is going to be charged every half year. And so since there are 2 half years in one full year, N would be 2. What do you think quarterly would give us an N value of? 4. Yep. Monthly would be 12. Weekly would be 52, and then daily would be 365, although a lot of banks take holidays off, and during those holidays, interest typically isn't charged. But just for simplicity, we'll assume that daily has an N value of 365. Any questions so far? So not only does compounding interest typically mean more money, the value of N can also affect, you getting even more money versus, a different value of N. So for different values of N, the value of A tends to be larger, okay? And we're going to see that effect with this upcoming example. It says here, $700 is invested at 10% compounded quarterly. Okay, that would be akin to an N value of 4, by the way. They want to know what is the value after a period of 6 years. And then we want to use some of those same parameters to see what the value would be if it's compounded daily, which that corresponds to an end value of 365. So there are two calculations that we're going to do for this problem. And let me set up workspaces for each of those. We have a quarterly calculation, and we have a daily calculation. What I typically do in problems like these is I make a little laundry list of all the information that we have, and I try to figure out like what number goes to what variable in the formula. The variables involved in the compound interest formula are A, P, R, N, and T. And I'll set up that list for the daily calculation as well. Now let's look at this first sentence. It says $700 is invested. $700 is either a value of A or a value of P. And based how it's phrased, or even, looking at the second sentence where, our question is at, what is the value after a period of 6 years? $700 would correspond to a value of P. That's an initial amount. So that's how much somebody's walking into the bank with. All right, so we're going to put 700 for P in each of these lists. And we're trying to figure out how much is in the account after 6 years. So we don't really know what A is, so I'll just put a question mark for that. 10% is a value of R, but we're going to want to use the decimal version of that instead, so 0.10. In the quarterly case, n is equal to 4, but in the daily case, n is equal to 365. And then this is all happening over a period of 6 years. So 6 is a value of t. So let me jot down the formula for compound interest, and I encourage you to do so as well. It helps with the memorization component. And we're going to fill these formulas in with all the values, and then maybe defer to our calculators to help us grind out the arithmetic. All right, so in the first case, P is 700. Then 1 plus R, so 0.10 over 4, and then to the 4 times 6. Okay. So I mentioned I'd explain those different components of the compound interest formula with, one of these examples, and I'm going to do that right now. So you're starting out with $700, and if you look at the expression inside parentheses, this fraction right here, 0.10 divided by 4, this is the percent that's used each time interest is compounded. And keep in mind, interest is being compounded 4 times throughout each year, but that doesn't mean that each time you calculate interest within the year that you're using 10%. Instead, when interest is being calculated each time throughout the year, the percent that's actually being used is whatever that comes out to be. I think that's 2.5%. Now, since there are 4 interest calculations, and this is happening for a period of 6 years, you do 4 times 6, you get 24, and that's actually what our exponent comes out to be. So basically what's happening is we're taking 700 and we're multiplying it over and over by this expression that's in the parentheses. We're multiplying it to 700 24 times. And that produces that layering effect. Now I'm going to write one more line here before we get to our calculator. I'll still leave that as 0.10 over 4, but just to make it easier in the typing component, 4 times 6 is 24, so let's write that out. Let's go to our calculators. $700, parentheses, 1 plus, let's type in 0.10 divided by 4. Be sure to close off the parentheses, otherwise your calculator thinks that your exponent is going on that fraction. And the power, type in 24. And we're looking at $1,266.11. Are you guys coming up with the same value? All right, cool. So we'll round to the nearest penny. And I'll invite you to do the daily calculation. All right, I'll jot down my solution. I'm getting something to the tune of $1,275.38. Confirmation on that value. All right. So we end up getting a little bit more when the interest is compounded daily. And from what I understand, I believe credit card companies charge interest daily. Now, same deal as with the quarterly calculations and explanation. If interest is being charged daily, it's not being charged 10% each time. Instead, every day, the interest that's used would be 0.10 divided by 365. And so it's a really, really small percentage, but the difference is kind of made up because the value of n is significantly larger, in this example versus, the quarterly example. But the net effect, is an increase in value, but not by a wide margin. They're relatively close in value, all things considered. But, more is more, though, right? So it kind of begs the question, if we increase n to as large as we want, does that mean that we're going to continue to get more and more money? And the answer to that is yes and no, and I'll discuss that on the next page. But first, let's take care of the last example on this one. It says find the principal needed to get $100 after 3 years, 5% compounded monthly. Let's make a laundry list. Do you think we have a value of A in this problem? That's right. $100 represents our value of A. And here's a little clue. It says find the principal. So that tells us that we don't know what the starting amount is. What's our value of R? Yep, 0.05. Value of N? Compounded monthly. And you've probably seen this coming a mile away. The value of T is 3. So we're going to fold all this into our compound interest formula, which let's write this down again. This time we'll replace A with 100. P we don't know, so we'll just have to leave it as is. That's actually going to be our variable to solve for. Then in the parentheses, 1 plus 0.05 over 12 raised to the power of 12 times 3. Let me simplify 12 times 3. And so the power on the base here is 36. And to get P isolated, first recognize that P is getting multiplied to that exponential expression. So what we could do to isolate P is actually divide both sides of the equation by that entire expression. Okay, that cancels it out on the right-hand side. And let me write P first. And when we write it as this fraction, that's going to be an exact value for P, but all things considered, I think we'll probably want to get a more practical answer by typing it in and rounding it. But do you have any questions before we get to the calculator? Is this interesting or what? I'll tell you what is interesting though. We got snow last night or yesterday. All right, folks. So let's be careful about how we type this in. First, punch in 100, hit the divide key, and we definitely want to be sure we keep those parentheses around the 1 plus 0.05 over 12. Okay, close those parentheses off, and then we'll hit the caret key to type in our exponent of 36. All right, let me know if you're getting something to the tune of $86.10. Anybody getting something different? Okay. So $86.10 would need to be put into the account in order for it to turn to $100 after 3 years, 5% compounded monthly. Now, Kevin, I noticed you put a comment in the chat about the 5% interest during the video. I have an idea as to why you might have said that, but did you want to explain?
Yeah, so every time I've gone to the bank to invest money, I think the interest rate was 0.05% or 0.5% compounded yearly, something ridiculously small like that.
Precisely, yep. Yeah, truth be told, these interest rates are they're fictional, I would say. Yeah, yeah. The interest rates are extremely low at the banks. I'll tell you what's doing pretty well though is cryptocurrency, especially Bitcoin. I'm not sure if any of you are, um, you know, investors in crypto, but Bitcoin, I believe, back in the early 2000s was somewhere around like $2 or $4 per unit, and I checked yesterday, it's around like 57,000 now per unit. So it is just crazy how that stuff works. Okay, well, let's move on. Yeah, Dogecoin. You know, a coin that I hear is going to be pretty popular is, I think it's called Pirate Chain, and the ticker name for it is RRR. Literally, RRR. um, it is pretty volatile. Yeah, yeah. It's pretty strange how the value of coin is determined. It's basically determined by people's perception of it. You know, if they think that a coin is going to be useful and valuable, then its value goes up. I mean, if any of you kind of follow around, yeah, if you watch Elon Musk, as soon as he mentions a crypto coin, boom, the next day, you know, it's skyrocketing. But I didn't know there was Tesla stock. That's pretty cool. Yep, yep. Let's talk about continuous interest. I kind of flirted with this idea on the last page. You know, as n increases, we saw that the value of a increases as well, but not by a large margin. But you know, it kind of begs the question: what happens if we want n to just grow larger and larger without bound? Well, if that's the case, you get something called continuous interest. And as n increases, what it means is that there's more interest calculations throughout every given year. And so if n is allowed to approach infinity, then it basically means that interest is being charged at all moments of time, hence the use of the word continuous. There is a formula that we can use under this assumption. It's the formula for continuous interest, sometimes referred to as the Pert Formula, which was, I don't know if they're still selling it, but a lot of people like to refer to this as like the Pert shampoo formula. I like to refer to it as the Neil Peart formula in honor of the late drummer of Rush, although his last name isn't spelled this way. But if we allow n to go to infinity, the compound interest formula transforms into this one right here, where it's p times a base e, and in its exponent is the product r times t. So the cool thing about this formula is you don't really need a value of n. The value of n is already accounted for. When n goes to infinity, that compound interest formula morphs into this, and that base, where it was 1 plus r over n, it transforms into the number e. And so just to discuss the formulas here, a is the final amount like before, p is the principal like before, and the rate and the time are, you know, same units as before. What's missing from this list is the value of n, and that's because we're assuming it to go to infinity. So this is the formula you use when your investment is getting, you know, hit with interest charge at all moments of time. So you might wonder, you know, when should I use this formula versus a compound interest formula? Well, just look for the keyword continuously. So if you see this example instructions, it says determine the balance of a $3,500 investment, 7% APR, compounded continuously. That's the key phrase right there, and continuously is the key word. And this is going to happen for 8 years. So let's go ahead and see how we can work this one out. We'll make a laundry list again. A, P, R, and T. We don't need a row for N, since that's missing in our formula. Now it says here, determine the balance of a $3,500 investment. Okay, so this is the initial amount of money, so that's a value of P. Value of R is 7%, but let's use that as 0.07. And this is happening for 8 years. That 8 represents a value of T. And we're trying to calculate how much is going to be in the account after 8 years have gone by. So let's fold this all into the Pert formula. Anybody here familiar with the band Rush, by the way? So this will be 3,500 times Tom Sawyer, you got it, E, and in its power, going to be 0.07 times 8. All right. If we want, we can multiply 8 to 0.07 to get 0.56. And then we'll punch this into our calculator and round it to the nearest penny. Okay, so 3,500. To get E on the screen, it's second ln. And in the exponent will be 0.56. Okay, so after 8 years, with a fictional APR of 7% compounded continuously, the initial investment almost doubles. All right, we went from 3,500 to a little over 6,000. So that's free money right there. How do you like that? But you guys coming up with the same number, $6,127.35? Alrighty. All right. I believe this is our last example for the section. How long will it take to double the investment of $500 if it earns 6% compounded continuously? So right off the bat, it tells us what we want to look for. We want to look for a value of T. Double the investment of $500. That's actually speaking to a value of A, and the 500 would be our value of P. And then, of course, 6% would represent our value of R. Now, if you look, it says compounded continuously. So that would mean we have to refer to the Pert formula. So let's go ahead and make our little laundry list again. So based on the phrase, double the investment of 500, what should our value of A be? $1,000. Yep. Our starting amount is 500. The rate R is 0.06, and T is, I don't know. But let's go ahead and see how we can figure that out. A equals P times E to the RT. Let's replace A with 1,000, P with 500, R with 0.06, and let's leave t as is. So we're solving for t, and it's in the exponent. So this is an example of an exponential equation, all right, something we went over last time. And remember, most important part is the start, where we have to isolate the exponential expression. So we want to get what I have boxed. We want to get that by itself before bringing in any logs. So what we should probably do is divide each side by 500 to make that happen. That'll give you 2 on the left, and then e to the 0.06t on the right. Now, we discussed 2 methods for solving exponential equations on Monday. We had the BS method and the log loop method. In this case, since our exponential expression involves the base e, I would recommend us use the BS method, where we're going to apply the natural log to both sides of the equation. Okay, on the right, the natural log cancels out e, and this will go back down on the ground. Nothing cancels on the left though, so we'll have to leave it as an actual log of 2. All right, what's our last step? Yep, divide by 0.06. So as an exact value, t is the natural log of 2 divided by 0.06. And I would recommend typing this into the calculator. After all, it does give us rounding instructions, round to 1 decimal place. Let me know if you guys are getting 11.6.